Yes. Okay. Okay. So welcome back to your Comp 335 tutorial. This tutorial is going to be slightly different just because I'm using a tablet instead of my iPad. So I'm going to be a bit slower to answer your questions because I have to switch back and forth. But other than that, it'll be the same. Okay. So topics for today, we're going to cover some of the stuff you saw during lecture last week. So we're going to look at deterministic PDAs and deterministic context-free languages. Then we're going to look at some closure properties for context-free languages, and then we're going to briefly introduce the pumping lemma for context-free languages because I know that it hasn't been introduced in lectures, so it's going to be a very light introduction. Okay, so deterministic PDAs and deterministic context-free languages. So what's the idea here? The idea here is just like in FAs. So in FAs we had DFAs and NFAs, where if you might remember, a DFA for every state that you had, you would have exactly the cardinality of your alphabet number of transitions. So what does that mean? That means like if sigma was AB, then for each state, you would have to have exactly 2 transitions, one for A and one for B, right? So that was a deterministic finite automaton. And then NFAs, we said, is everything, everything including a DFA, but we can also have more than sigma transitions, more than cardinality of sigma transitions. We can have, so we could just have one. It could be underspecified, it could be overspecified, and you can also have lambda transitions. Right, so that was non-determinism for FAs. And just as a reminder, we had shown that the languages that are accepted by DFAs is equal to the languages accepted by NFAs, meaning that DFAs and NFAs have exactly the same power. So they have the same power of accepting exactly the same languages, right? So now that we go sort of one level higher in computational power, where we have PDAs. So PDAs. So remember, this is kind of a refresher, but what's a PDA? You know, it's almost the same as an FA, except that, so you could say it's kind of like an FA plus you use a stack, right? So you just add some memory to your machine, and that, as you saw, allows you to accept more languages than you can with FAs, okay? And so far, what we've considered are NPDAs, right? So I've kept saying sort of implicitly that these are, so I've been saying they're PDAs, but actually they're NPDAs, okay? So the reason why we say they're NPDAs is because really implicitly what your machine is doing is it's guessing sometimes it's guessing the correct solution. So what do I mean by guessing? So if, for example, if you remember the language W such that W is equal to WR, right? So the language of palindromes, what was going on here? Well, what you were doing is you had your input string. So imagine your input string was A, B, B, A, right? So there's a question. Yes, good. So what was going on here? Well, your machine was running through, and as someone just pointed out, they were able to correctly guess that, okay, I should stop pushing here, and now it should start popping here, okay? But so when you think about it, a computer doesn't really guess, right? So there's some kind of magic and non-determinism that's going on here, which actually allows you to accept more languages than if you were not allowed to guess. And that's where we go to deterministic push-down automata. Essentially, in a nutshell, so we're going to look at the formal definition in a second, but in the nutshell, you cannot force your machine to guess. Basically, that's it, okay? But now, so say it like this. So there's another question, but should not, yeah, so I mean, the guessing also works if this is odd length palindromes. So if you had something like AAB, A, B, AA, then your machine is still an NPDA because it still needs to somehow guess that you have to stop here and then use a transition here and then keep going here and popping. So there's still a guess, an implicit guess that's going on because you're kind of guessing almost the half of the string, okay? So there's still some guessing going on here. So that's why actually, so we'll get to that later, but that's why actually this can't be accepted by a Dpda, okay? Because as I said, informally, a Dpda just cannot guess, okay? But so let me just look at the formal definition and then maybe I can answer more questions. So what's the formal definition of a Dpda? It's the same thing as an NPDA, so it's the same 7-tuple, except that now we have restrictions on our transition function delta. So what are the transition function? The transition function restrictions, yes. So they are that for every triple state, symbol in the alphabet, union lambda, and symbol on the stack. So for every such triple, the transition when you're in Q, you read an A and you see B at the top of your stack, you can have at most one element, or in other words, at most one choice. Okay, so what does that look like? Let me just zoom in a bit. So that just looks like, let's say you're in Q1, right? You're essentially not allowed to say, if I'm in Q1 and I read an A and I see a B at the top of my stack, then I don't know, let's say I pop it here and I go to Q2. So if you have this, then you're not allowed to do this. So if you see an A and you see a B, well, in this case, you know what? I'm gonna push an extra B and go to Q3. So this, because it's a deterministic PDA, you can only have one choice for every possible configuration you have. So that means that it's not allowed for you to have a second choice here, right? Because if you're in Q1, you read an A and you see a B at the top of your stack, you have two choices. Namely, you can pop and go to Q2, or you can push a B and go to Q3. Okay, so that's not allowed. You only want one choice. Okay, so that's the first restriction. The second restriction is a bit more abstract. It says that if you're in Q and you're reading a lambda and you're reading something on your stack, if this is a transition in your state, then any other transition that has that's reading a symbol instead of lambda cannot exist. Okay, so what does that mean basically, like pictorially? Let's say you're in Q1 and you have this transition, don't read anything and don't touch your stack, okay? So if you have this, then you're not allowed to have something else with the same stack symbol. Okay, so basically you're not allowed to have something like A, so you read an A and then you see a B and then you do nothing. Okay, so why you're going to say, oh, well, it doesn't really look like there's two choices here. Okay, but actually there are, because if you're in Q1, so let's say you just got to Q1, right? You just got to Q1, then you can either do nothing, right? You can either do nothing and go to Q2. And then maybe in Q2, there's going to be an A transition. Or you can read an A here, do nothing to your stack, and then using this lambda transition, because I haven't touched my stack, I can then go to Q2 sort of again. So there's two ways of going to Q2 if you're reading an A. You could just not read it and go to Q2 directly, or read the A in Q1 and then go to Q2. Okay, so actually here there are two choices. And the fact that there are two choices means that your machine has to guess, which means that it isn't a deterministic PDA. Okay, so that's the definition, right? Of course, whenever you see a definition like this, it's very abstract, so that's why we're going to see an example. But maybe before the example, let me just say something else, is a language is said to be deterministic, context-free, if and only if there exists a Dpda M such that L is accepted by M. Okay, so if L is a deterministic context-free language, right, then that means that L is a context-free language, right? Because remember, L is a context-free language if and only if there exists a context-free grammar that generates it, and if and only if there exists a NPDA that accepts it. But a Dpda, just like a DFA is an NFA, a Dpda is an NPDA, right? Because it's just not using the non-determinism of the NPDA. So that's why if L is a deterministic context-free language, then L is also a context-free language. The converse, however, is not true. So in other words, what does this mean? This means that there are languages L which can be accepted by an NPDA, but cannot be accepted by a PDA, by a Dpda. So I know you saw this before, but I like to emphasize it in the tutorial as well. If this is the set of languages that are accepted by deterministic context-free languages, then it's a subset of the languages generated, or the languages that are just context-free languages, okay? So something that's in here but not in here would be L is W3, R, not 3. So the languages of palindromes is context-free, but it's not deterministic context-free. Okay, so I hope that's clear. As I said, this definition isn't super obvious, so that's why we're going to look at an exercise, and you're going to see it's not that. Really, you just have to be careful with the lambda transition, and then the rest is going to be pretty straightforward. So we have the following exercise, and we want to know if the following PDA is a Dpda. Okay, so to do that, you just have to essentially go through all of the transitions and check that delta QAB, so the size of this is at most 1, and if delta Q lambda B is not empty, so in other words, so this is, I think this is word for word what the lecture says, but it's actually a good definition. If this is not empty, then you have to make sure that delta QAB is empty for every A in your alphabet. Okay. Okay. So we start at Q0. There's only one transition from Q0 to Q1. So that's just, you're checking that you have a $sign. So there's no choice here, right? So this is okay. If you're in Q1 and you read an A, so is there any other transition where you read an A? Yes, there's this one. okay? But that doesn't automatically mean that it's an NPDA because the stack symbols are different. So in fact, it's not like you're guessing here. The choice is deterministic. If you read an A and you have a $sign at the top, then you know that you have to use this transition. If instead you have a C at the top, then you need to use this transition, okay? So the choice is fixed, it's deterministic. And then again, if you're in Q1 and you read a B, there's no other transition for B, right? So you can just say, well, this is okay, and you can just go to Q2, right? Now you're in Q2. So what are the transitions that come out of Q2? There's the one where you read a B, and there's one where you read a lambda. Okay, so remember, if there's a lambda here, then you have to be extra careful. So what does it say what does the definition tell us if there's a lambda transition? It says that there shouldn't be any other transition that has the same stack symbol here. So I don't really care what's going on after the stack symbol, but if it has the same stack symbol, then it cannot have a different symbol in the alphabet. So it can't have, for instance, A or B. But if we look here, if we look at the other transition, that doesn't happen, right? So that doesn't happen because when you read a B, you need to see a C at the top of your stack, okay? So I'll get to your question in a second. So what that means then is that because this rule is satisfied for this transition here, right? And there is no other transition for B, then this is going to be deterministic. Question?
Yes, if
Yes.
the last transition was a lambda goes to lambda, then that would not be satisfied, right?
If it's
Instead of the $sign, there's a lambda at the last transition, then the condition, the first condition, the second condition will not be satisfied, right? Because it's going to be empty.
So I remember someone else asked me that question. Yeah, so so in this case, you're right, yes.
Okay.
But for instance, if you were here, if you had something like this, then this is okay. Because I mean, it's useless, right? It's not doing anything, but
But it shouldn't be the last thing, right?
yeah, well, it shouldn't, because here you have a choice, right? You can either when you read a B and there's a C at the top of your stack, you can either pop it and stay in Q2, or you can pop it and then go from Q2 to Q3. So you have two choices. Okay.
And for the part for the Q2, there's BC goes to lambda, and then there's BC goes to lambda. It's not like a redundancy there, or just when we're moving forward.
Where, sorry, this transition?
But there's two ways to come back to Q2. There's BC lambda, and then there's BC lambda in a loop, right? Isn't that the same stack?
Oh yeah, this machine doesn't, I don't know what this machine does. This was just to illustrate the transitions.
Yeah, I understand, but wouldn't this negate the fact that it is a Dpda? Because we have B and then we have the same stack symbol for both.
Yes, but this is, so you're talking about, just to make sure, you're talking about this one and this one, right?
Yes, exactly.
Okay. Yeah, no, well, that's because this one is to go from Q1 to Q2, and this is once you're in Q2, how do you transition from Q2?
So we're comparing just our current state with the forward state, right?
Yes.
It's not our current state with the previous state.
Yes, exactly.
So this wouldn't hurt. This would still be a Dpda with redundant.
Yeah.
Okay.
Yeah.
Thank you.
Yeah. Good question. So there's another question in the chat. If in Q2 there is no loop, right, then it is also okay. Yes, it is. Yes. That didn't sound like a question. I think that was a statement. So yes, it is okay. Okay, so very good. Now there's a couple questions here where I mean basically the questions that you naturally ask. So what if we replaced Q1 BC to Q2 lambda with Q1 AC to Q2 lambda? So basically, which one is that? Q1 B, yeah. So if you replaced this one here with, I'm sure someone already answered, with A, C goes to lambda. So did someone answer? Yes, very good. It would not be a Dpda. Why? Because for Q1, when you read an A and there's a C at the top of your stack, and there's an A, you read an A and there's a C at the top of your stack, you have two choices. Either you can push another C and go back to Q1, or pop that C and go to Q2. Okay, so you have two choices. So no, it's not a Dpda. It's because you have a choice. So as soon as you have a choice, it's not deterministic. Okay, so very good. It looks like you guys are getting it. And then the other one here is similar question to before. If we added Q2 lambda C, it goes to Q3, and essentially you don't touch your stack. So basically, if we did, you read a lambda, there's a C at the top of your stack, and you pop it. Well, now it's this rule that is being violated. So that the rule that's being violated is here there's a C at the top of my stack and there's a lambda that I'm reading. Well, here there's a B that I'm reading and there's a C at the top of my stack. So you can't have that because the rule says that if you're reading a lambda and there's a C at the top of your stack, then you can't read anything else with a C at the top of your stack. Okay, so this would also be no. All right.
So
Yes.
to sum up, we can say that for it's two conditions. It's if we have the same top of the stack and then
Yes.
it's doing something else, and if we're reading something different and it's still doing something else, right?
So I'm a bit afraid of saying I like the formal definition because it's very concise. But yeah, it's essentially if you have something at the top of your stack and you can either read something or read nothing. So meaning you can either read nothing or read something, then yeah, that's not deterministic. Yeah, that's not deterministic. Or the second thing that you said was, sorry, what was the second thing you said?
If we have the same top of the stack and then it's doing something different.
If you have the same top of the stack, and yeah, that's also, that could also be something.
BC lambda and then let's say BCA or BCX.
Yeah. Yeah, good. Yeah, exactly. Yeah, so informally, that's also what you could say. Yeah, very good. So there's a question. Can you please repeat the last one? So, oh, I don't know what the last one is. Okay, so this one.
We add the.
Sorry.
The one where we add the transition.
Oh, you mean this one?
Yeah.
Okay. Yeah. Sure, no problem. Let me just erase. I'm sure this is very confusing because. So again, because I'm not using the tablet, it's very messy. I apologize. So I'm adding this transition here. Okay. So essentially, this is not allowed because now I'm reading a lambda. So because I'm reading a lambda, then I see a C at the top of my stack. There can't be any other transitions that have a C at the top of my stack and don't read a lambda. So that would be this, right? Because now you have, so actually what's going on here is you have two options. Either you can go to Q2 and then read a B, or you could use that lambda transition. So you have two choices, and sort of by definition, that's why you can't call this deterministic. So the rule is just that, so just to make it even simpler, the rule is just that if you have a transition where there's a lambda, so it's always just going to be the lambda for this rule. And you have something, you don't really care what's going on here, but you have something at the top of your stack. There can't be any other transition here that has a symbol A and then the same thing at the top of your stack. So as soon as you have the same thing at the top of your stack and this A is different from this lambda, then that's no bueno. It's non-deterministic. Okay, great. Very good. So okay, so that was an exercise in determining if the machine is a Dpda or not. So now let's go to an exercise where, where we want to show that a language is deterministic context-free, that is, we want to find a Dpda M, a Dpda M such that L of M is equal to L. Okay, so I'm sure someone's going to ask me what's the strategy here. There is no real strategy. You just have to kind of try a bunch of different things and then see if you can get your transitions to be deterministic. There isn't kind of a fixed rule where, you know, oh, if it's this kind of language, then you have to have this kind of strategy. You really just have to do a couple of examples and try to get a knack for it. I know that's obviously not obvious, but that's unfortunately the reality of this. So let me just answer. Same thing, would it be okay to choose a string and try to make it general from there? So what do you mean by that?
Would it be okay to choose a string that is accepted by the language and then try to make it more general in terms of accepting the condition?
Yeah, that's one strategy. So that's the strategy I was going to use. Okay. So actually, the first thing I want to do is I want to show you a quick way, of doing it sort of the wrong way, which is not the wrong way just because you want a deterministic PDA. So your first instinct might be to create an NPDA. And I'm going to show you why that kind of goes wrong. So as you suggested, let's say you take, for example, A4, B7. So this is part of the language, right? Because if n is 4, then 7 is greater or equal to 4 plus 3, which is 7, right? So this should belong to L. So what's going to be the strategy here? Well, one strategy you could use is you could notice that, oh, well, this is like A4, B4, and then B3, right? Or actually, it could be anything greater or equal to 3, really. It could be B4, B5, and so on. The only thing is it can't be B0, B1, and B2, right? Because then you would get M would be strictly less than n plus 3. Okay, so the first idea that you could think of is, okay, I'm just going to use the ANBN subroutine, basically. And then once I finish that, then I'm going to check that I have at least 3 B's. So I'm going to do this quickly. So I'm going to push, I'm going to push a $sign. Even though you don't need to, it just makes me feel better. Then I'm going to read all of my A's. And for each A that I read, I'm going to push an X. Okay, so let's say I have 4 A's. I'm going to push 4 X's, right? So I'm going to use that. And now what I'm going to do is I'm trying to say, I'm trying to find a way to show you that this is, no matter what you do, it's going to give you an NPDA. So let's say I'm not going to use a lambda transition because that would automatically give me, so if I use this, right, that's automatically not a DPDA. So instead, I'm going to try to be deterministic and say, oh, well, once you see a B, you're going to start popping, right? You're going to start popping. So for instance, here you have B7. So you pop the first X. Okay, so you're here now, you've popped the first X. So now what you need to do is you need to pop 3 more X's. So that's what's going to happen here, right? For the, you're going to read a B, and for each X, you're going to pop it. Okay, so how do you know that you're done? You know that you're done when, wait a minute. Yeah, you know that you're done when you're at the $sign, right? So done meaning that you have the same number of A's so far as B's. So you have 4 A's and you have 4 B's, right? But now you need to have more B's, right? You need to have more B's. You need to have at least 3 more B's. So what do you need to do? You're actually forced to read a $sign, to read a B and then read a $sign at the top of your stack, right? So, okay, so far it's actually not looking like it's an NPDA. Don't know if anyone disagrees with that, because at first I initially thought this was an NPDA, but so you're going to read the first extra B, then you're going to read the second extra B, then you're going to read the third extra B, and then once you're there, once you're here, then you can start accepting, right? Because what does this mean? That means that you read the same number of A's as B's, and then you have an extra 3 B's, right? But now I'm not done, because now this would just accept AN, BN plus 3. But I want to accept AN, BN plus, so actually I want to accept AN, BN plus K for K greater or equal to 3. So that means that I want to accept more than 1 B. So I can just loop a bunch of B's here. So, yeah, oh, I see. Okay, that's why. Okay. Okay, so I'm going to explain something in a second, but let me just answer your question. Why did you say that the lambda transition will make it a non-deterministic PDA? So, yeah, I think I misspoke there. What I meant to say was, so if you had a lambda transition here, right, then this would be okay, because like what I'm saying is, if instead of this, you had this lambda transition, then that would be okay, because you're reading this $sign only for this transition. So that's fine, okay? Although this doesn't give you the correct language, but that would be okay. So, yes.
I think the lambda transition, when you first said it was gonna make it one PDA, was in the transition right before that.
Yeah, here, right?
Is it
Yeah,
because of the A lambda X?
Yeah, so what I meant to say was something actually really dumb, was if you just have lambda lambda. So clearly that's not going to make it deterministic, because you have a choice here. But if even for instance you had done something like lambda x lambda, then that would also be fine, because you're reading an X here and you're not reading an X anywhere else.
Yeah, but aren't we doing an NPDA and it is fine to have a choice?
Yeah, no, that's why initially I wanted to show you, so I kind of messed up my example.
Oh, okay, because it kind of gave me like a
yeah,
brain
no,
thought.
sorry about that. This is actually, so this is an NPDA, but actually it's even better. It's a DPDA, because there are no choices. So I was trying to show you a way of being like, oh, you know, let me make an NPDA, and then I show why it's not. But
So
anyways, okay, I
you're
messed
saying
that up.
that a DPDA is a subset of an NPDA?
Well, the languages accepted by the Dpda
Uh-huh.
are a subset of the languages accepted by an NPDA. And if you have a Dpda, it's also an NPDA
Okay.
because a Dpda is just a more restrictive NPDA,
Yeah, makes sense
right?
because you have more choices of an
Yeah.
NPDA. That was a dumb question.
No, it wasn't. I mean, I messed up this exercise, so sorry about that, everyone.
Okay.
So yeah, this is actually a Dpda to be more precise. So someone had a question. It looks like someone answered the question. Yeah. So the transition. So just to reiterate, $sign just means that you keep nothing in the stack. Don't we need to pop all the symbols in the stack? No. So you don't need to do that. You can if you want to, but it's not necessary. So particularly, actually, in this case, if you had something like yeah, I don't want to confuse anyone, but I'll give a different example. If you had something like B $ lambda, and then you finished here, then that's essentially the same. It's equivalent to doing a B $. The only thing that's important to remember is that once you do this, then your stack is empty permanently, right? So that means that, so remember, once your stack is empty, you can no longer use it. You can't have any more transitions with an empty stack. Okay, so the only reason why sometimes people do this instead of this is because you know, oh, maybe at some point I want to add something to this final state, and so then you could do that here. You could do that here because your stack isn't empty yet, but you could not do that here because once your stack is empty, you can't have any more transitions. Okay. All right. So I hope that's clear. And yeah, so as I said, this is a Dpda that you can arrive to an accepted state with, yes, very good. Also, that's also true. You can, yeah, there's no, like, if your stack has a bunch of stuff and you go to a final state, then that's okay. You can, I mean, it doesn't matter what the contents of your stack are at the end. It could have a bunch of stuff. It's just that usually, like formally, whenever you do a problem, you're using your stack. So at some point you're going to want to empty it. So that's why typically you typically see a $, but it's not like an obligation, because sometimes, like I think in the previous tutorial exercise, there was one where I wasn't checking that there was a $, I was checking that there was an X or a Y, right? So it's not necessary. Okay. Any more questions about this? Because it looks like, I don't know, I don't mind taking more questions. No? Okay. All right. So, oh, good. Okay, very good. All right. So again, I apologize for the. Usually my handwriting is a bit better, but with the drawing tablet, it's much worse. So sorry about that. Maybe do I want to say something else? Yeah. So another, just a quick. So I won't do this in detail, but another way you could have done this, this an b m for m greater or equal to n plus 3, is you could have actually just started with 3 x's at the top of your stack, and then you would have forced, essentially, you would have done the an bn stuff, right? You would have done your an bn stuff by pushing here and then popping here, okay? And then once you were done that, then you would just need to pop these x's to make sure that, you have at least 3 b's, extra b's, and then you could have kept going by creating more, by creating extra transitions. So essentially, I'm saying that there's more than one way of doing this, basically. I'm sure everyone knows that by now, but there's not just one answer. Okay. Yeah, so a quick word. So I've already said this, but very important, NPDAs and DPDAs are not equivalent, meaning that they do not have the same power to accept languages, basically. Okay, so the set of languages accepted by DPDAs is a proper subset of the set of languages accepted by the NPDAs. And so one example is the palindromes. As I said before, the palindromes, you need to guess the middle. So that's an informal way of saying why it can be accepted by an NPDA, but not by a DPDA. Okay. So now the next topic is closure properties of context-free languages, which is something else that you saw in lecture. So what are the closure properties of context-free languages? So it's very similar to regular languages. You know, you have two context-free languages in this case, and you have an operation. And we say that if L1 operation L2 is context-free, then context-free languages are closed under that operation. Okay, so there's a couple of results that I'll just remind you from lecture. The union of context-free languages is context-free. So the quick and easy way of proving that was, remember, you just if you have a context-free grammar for this, and this is your start symbol, start variable for L1, this is your start variable for L2, then you just use this this pipe symbol for saying the union of the two grammars gives you the union of the two languages, in particular for this. So that's not always true, but it is for here. And then the concatenation, that was just if you concatenate the two variables, and L1 star, don't know, am I going to get this right? So I think it was something like S1 lambda. So essentially you can just repeat, you can repeat the grammar for L1 an infinite number of times, and that's going to allow you to essentially continue to concatenate any number of L1s. So I think it was this. So I might be wrong, but pretty sure it was. So then, or maybe it's not. Let me check.
I think maybe they're flipped. I think it's S, S1, and then S.
Yeah, yeah, no, actually,
on the
that
left.
Sense.
Yeah, it has
no,
to
that
be
makes
left
sense.
derivation. Okay. But S1 then just S.
Yeah, sorry. Yeah.
Okay. Yeah, I think that's it.
Yes, very good. Thank you for the correction, because I wasn't sure.
Oh, thank you.
So that's for closure properties. Okay, so damn it, someone asked, does it matter? It's a good question. So what is S1? S1 is the start variable for the grammar G1, such that L of G1 is equal to L1. So you have this. So I'm thinking out loud. So if you do something like S gives you S, S1. Does it matter?
It doesn't seem like it would, but then in the notes it was written this way, so maybe it does.
Yeah, so because the reason why I don't think it matters is because if you reverse these two, you're just doing the reversal of like a bunch of the same languages, right? So it's not like it's different for
Would it be problematic if we had another S that goes to, let's say, S2, and then how would we know if it's gonna go to the right S? Like if we had S and then S,
right.
S1 and then S2, right?
S.
So if we had S,
yep.
Yeah, S2, exactly. How would we know that S would respect going to S1 instead of S2?
You wouldn't. So that's why you wouldn't put it in there.
Yeah, okay.
Yeah, but actually, to be honest, I don't think it matters because because like if you just look at the high level derivation, it would be like, let's say you wanted to compose yourself of 3, like you wanted L1, L1, L1. Then if you wanted to derive it here, you would do S1S, then S1, S1S, and then S1, 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 and then lambda, right?
Oh, yeah.
But I mean, that's the same thing as doing S, and then S, S1, and then S, S1, S1, and then S1, 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 and then a lambda. So I actually don't think it matters for this particular case. So to answer Ryan's question. Okay, but good question. More questions? Okay, no, just thank yous. Okay, so then there are other closure properties which are essentially kind of ones that don't hold, which you have to be pretty careful about because you can get sort of tricked by these. So the context-free languages are not closed under the intersection and the complement, okay? So a reason why the intersection is not, why they're not closed under the intersection is because you're going to see in lecture that AN, BN, CN is not context-free. But if you take AN, so this is the same example as in your slides, I just want to remind you. If you take AN, BN, CM, that's for sure context-free because you can do AN, BM with a ASB grammar, and then this C is free. It can be whatever you want. And then you can have AM, BN, CN. So this is also context-free. But if you take their intersection, right? So if the context-free languages were closed under intersection, then if you took their intersection, then AN, BN, CN would be context-free, which would be a contradiction. Okay, so that's one reason why it's not true. The complement, I don't think they actually gave you a counterexample for why, because actually it's a bit trickier to think of a contradiction for the complement. But do we think that the difference is or isn't? Well, I mean, it's under not closed, but L1 minus L2, if L1 and L2 are context-free, is that going to be context-free? So does anyone think? No, okay. So very good. It's no. Why is it no? Let's say you had, yeah, okay. So L1, so that's the right idea. Okay, what is, yeah, so that's the right idea. Let's say you had L1 was, so I'm just gonna give you a quick contradiction. If L1 was sigma star, right? Sigma star is regular, right? If it's regular, that means it's context-free, right? Okay, so now suppose that L1 minus L2 was closed under context-free languages, right? Now let's say I did L1 minus L2, where L2 was context-free, and L1 is also context-free because it's regular. But now L1 is sigma star, right? And so you have L1 minus L2 is sigma star minus L2, which is what? Well, that's just L2 complement. So, so that would mean if we assume that it is closed under difference, that would mean that this is context-free, which would mean that this is context-free, which would mean that this is context-free, which would mean that all context-free languages are closed under the complement, but that would be a contradiction because of this. Okay, so that's a quick reason for why that's not true. Okay, and for there's another interesting closure property, which is for when you have a context-free language. So L1 is context-free, and L2 is regular. So this is useful when you try to prove that something is context-free. It turns out that the intersection of these two is going to be context free. And the same thing is true for their difference. Why? Because L1 minus L2 is L1 intersect L2 complement. L2 complement is regular because regular languages are closed under complementation. So that would mean that L1 intersect, so you have L1 context free, intersect something is regular. So that would mean that the whole thing is context free. Okay. So let's do this exercise, and then don't think I'm gonna have time for pumping lemma. I mean, you didn't really see it in lecture, so I can just maybe briefly talk about it. So there's an exercise here that sort of is based off the previous closure properties, where we want to show that the language L is context free. And L is a and bn for n is not a multiple of 3. So one way to do this is you could just create a context-free grammar, okay? But you know, you have to consider not multiple and things like that. To be honest, I didn't really think about it. Maybe it's simple, but there's a much faster way of doing this if you just want to prove that it's context-free. Okay, so the way to do that is, excuse me, you're gonna want to take L1 a regular language and L2 a context-free language. You're gonna want to intersect them so that you can get a and bn such that n is not a multiple of 3. So very good. It looks like someone already guessed something. So what can L2 be? So L2, because you know I have, you know, it's a hint that I have a and bn. So a good choice is going to be a and bn for context free, right? So I know this is context free. I don't need to prove it again. And then what do I need to intersect it with? What do I need to intersect L2 with to get this? Well, I just need to control these ends here. So a and bn, but what are the restrictions? So someone is saying an bm, but I need restrictions on n and m. So what are those restrictions going to be? Yeah, n greater than 0. Yeah, I agree. But more specifically, how are you going to want to not make it a multiple of 3? Because remember, here, what do you have? You have, yes, very good. Here you have lambda, AB, A2, B2, and so on. So you just want to take these guys and you want to intersect them with something so that you only get AB, A2, B2. You're going to skip A3, B3, then get A4, B4, A5, B5, and so on, right? So what you're going to want to have here is you're just going to want your A's to not be a multiple of 3. So in other words, so someone wrote, yeah, so you could say n mod, that's a nice way of writing it, n mod 3 is not equal to 0. And the same thing for m mod 3 is not equal to 0. So then these are A's and B's such that, you know, the A's don't have a multiple. There isn't a multiple of 3 A's and there isn't a multiple of 3 B's. So when you intersect that with A and Bn, then you get the same number of A's as B's with the extra condition that n mod 3 is not equal to 0 and m mod 3 is not equal to 0. So this would give you this. Okay. The only thing that you would kind of have to do is you need to show that L1 is regular, right? So what's a very quick and fast way of showing that this is regular? Well, you could just create an FA, right? You could create an FA where, let's say I create a lambda transition, and this is going to be equal 0 mod 3. This is going to be 1 mod 3. Then you have an A. This is going to be 2 mod 3. So I hope everyone sees where I'm going with this. So I don't want 0 mod 3, right? I don't want a to the n mod 3 to equal 0. So I'm not going to create a transition to this guy here, which is going to be the same machine. So the same machine where this is mod 0, this is mod 1, and this is mod, sorry, not mod, this is 0 mod 3, this is 1 mod 3, and this is 2 mod 3, okay? So the same thing, so I'm not going to send this to here, but I am going to send this to here, and this to here, right? So hopefully you see what's going on. I'm going to have a non-multiple of 3 A's, so either 1 mod 3 or 2 mod 3 A's, and then from either of those, I'm going to go to the same machine here where you get mod 3 B's, and now what are going to be the states that I'm going to accept? Well, if this is 0 mod 3, this is 1 mod 3, well, this is good, right? Because I don't want a multiple of 3. So I'm going to make this a final state, and I'm going to make this a final state. So then this would be an FA that accepts L1. So L1 is regular. Trying to think if there was an easier way. There's probably a much easier way of doing this. Like, for example, with a regular expression. Yeah, I can't off the top of my head. I feel like with a regex, you could maybe make this cleaner, but you know, this works. So it shows that L1 is regular. And so now you have that L1 is regular, L2 is context free. And so the intersection gives you the language you're looking for. And by closure properties, this is going to be context free. Okay, so that's what we have for that. So I'll leave it to you. I'll leave it to you if you want to make this nicer, if you have any time. But I mean, this would be accepted, right? I mean, as long as it works. So that was for the exercise of showing if something is context free using the intersection, an important closure property. The other one is a true false. So I know this is everyone's favorite type of questions. So we have two claims here, and we want to know if they're true or false. The first one is saying that if L1 is regular and L2 is context free, but not regular, then L1 union L2 is context free, but not, well, I don't know why I just rewrote it. Okay, so what are we thinking here? Ooh, someone said true, okay. So any other guesses? No other guesses? So, okay, so let's see, what happens if L1 is sigma star? Well, what happens if L1 is sigma star? What is L1 union L2? Hope everyone's saying this in their head. L1 union L2 is sigma star, right? So sigma star is a regular, right? Which is not the same as being context free, but not regular. This specifically says that L1 union L2 should not be regular. But sigma star is regular because remember, this is an FA that accepts sigma star. It's an FA, so it's regular. However, yeah, so no, this is already a counterexample. L2, if you make L2 context free, so for instance, if you make L2 AN BN, n greater or equal to 0. So this is regular. This is context free, but not regular. But because sigma star is the universal set, if you union the universal set with any other set, you get the universal set sigma star. And sigma star is regular, which is different. So I know it's confusing at first, but okay, so what is this, just visually, what is this saying? If this is a set of regular languages, and this is a set of context-free languages, then this is saying that L1 union L2 should be here. It's saying that it cannot be here. But what I've shown is I've shown that I can take an L2 here, an L1 here, and then once I take their union, I can actually go back here. Okay. Okay, so maybe, yeah, the graph I think maybe helped. Would 1 still be true if we had intersection instead of union? Good question. So if L1 is regular, L2 is context-free. Okay, so if L1 is regular and L2 is context-free but not regular, L1 intersect L2 by the closure properties we just showed would be context-free. The question is, would it ever be regular, basically? So yes, it would. If L1 was the empty set. If L1 is the empty set, then the empty set intersect any context-free language is, yes, it's going to be context-free, but it's also going to be regular. So, but not regular would be not true. Okay, good question. The other, okay, so, okay, I was gonna say there's a different type of question where it just says context-free and it forgets about this, but that's this question here. So let's look at that. Okay, where can I write? Let me write, let me move this here. I'm gonna write here. So, okay, what does 2 say? 2 says L1 is finite and L1 intersect L2 is context-free. Then L2 is context-free. Okay, so if L1 is a finite, means it has a finite number of elements. So why are we saying, this is kind of weird, no? Why are we saying that L1 intersect L2 is context-free? Isn't it kind of weird that, okay, okay. So no one fell into my trap. So I was gonna say, oh, well, isn't it kind of weird that it's here? Well, no, but if it's context-free, it could also mean that it's here. So that would be okay. So as someone pointed out, L1 intersect L2, well, the intersection is also going to be finite. Because if you have a finite set and you intersect it with anything, you can only have at most the number of elements in the finite set, right? You can't have more, right? Because there's nothing more in the set. So that means that L1 intersect L2, yes, it's context-free, but it can also be, it's in fact finite. So for sure, this is true. Okay, so we have this. Then it says that L2 is context-free. So what do we think? Is this true? So it's saying that if we draw, okay, so someone answered. If we draw, let's say L1 is finite, so it has to be regular. L1 intersect L2 is context-free, so actually it's in here because it's finite. Actually, context-free is very loose. So this is a set of regular languages. This is context-free. Is it possible for L2 to be all the way here? Well, it doesn't seem obvious, does it? How can you go sort of from this tiny set here, even though it's infinite, to this bigger set here? Well, let's take an example. Let's say L2 is AN, BN, CN for n greater or equal to 0. You're going to see again in lecture that this is context-free. This is not context-free. So what happens? What's the result of, let me try to move. Yes, okay. Let's say L1 was finite. And well, we know L1 is finite. What does L1 intersect L2? Is this going to be finite or infinite? Let's see, finite. Okay. Yeah, I want someone in particular to say, okay, it doesn't seem like, because someone said true. This is actually going to be finite, okay? So the fact that it's finite means that these two conditions here, L1 is finite and L1 intersect L2 is context free. These are true. However, I picked L1 such that it was AN, BN, CN, right? I picked it here. So it is not regular. It is, sorry, not context free. So this is false.
I have
Okay,
a
so-
question.
Yes.
Didn't we say earlier that for any context-free language, let's say L1, and any regular language L2, the intersection of L1 and L2 is context-free? And since L1 is finite, it means it's regular. So regular intersecting a context-free means that
yes.
L2 is a context-free, right?
Yes, but what, so is that actually what statement 2 is saying? L2, statement 2 is saying L1, so imagine this was regular.
Okay.
This, imagine instead of finite. So L1 is regular and L1 intersect L2 is context free, then L2 is context free. So this is not the same thing as L1 is regular, L2 is context free, then L1 intersect L2 is
Oh,
context free.
what you mean, yeah.
Yeah, because you're taking this and you're putting it here and you're taking this and you're putting it here.
Yeah, makes sense.
So the converse essentially, even though it's not exactly the converse, is not necessarily true.
Okay.
Good?
Mhm.
Okay, very good. All right. Okay, so those are the, I don't know if there are more questions for that, but let me just, yeah, okay. So I'm not gonna have time to go over this, but okay, because I'm obviously already going over the time and I don't like to keep people. So let me just say a quick few words. So because you're going to see this in lecture anyways. So the pumping lemma for context-free languages is very similar to the one for regular languages, except that now your decomposition is going to be slightly more complicated. So the lemma says that suppose L is an infinite context-free language. Then there exists an m greater than 0 such that for a string in L with its length greater or equal to m. So far it looks like the pumping lemma for regular languages. So far. It gets a bit complicated in the next part. W can be decomposed as u, v, x, y, z. So into 5 parts instead of 3 parts, where these 3 strings have length at most m, and these 2 have length at least 1. Okay, so you have that decomposition such that if you pump up or down the 2 v and y's, up or down with the same i's, then for all the i's here, that should be in L. Okay, that's what the statement is saying. And so essentially, when you're doing a pumping lemma proof for context-free languages, again, you can only show that the language is not context-free. And so you can only use the pumping lemma to show that it's not context-free. And the process is very similar as before. You assume for the sake of contradiction that L is context-free. You pick a string. So again, this is probably the hardest part of the pumping lemma here, is that you need to pick a particular string such that the length of that string is greater or equal to m. And then what you do is you decompose. So you decompose W into u, v, x, y, z, where you're going to say, I want vxy to be at most m and vy to be at least 1. Okay, so you're decomposing kind of like the regular language, but a bit more complicated. And in fact, what you're going to see in lecture is that you're going to have several possible decompositions. Okay, and you're going to have to pump up or down. So for each possible decomposition, you're going to have to pump up or down sort of to find a contradiction. And if you do that for every possible decomposition, then you know for any possible decomposition and for sort of particular i's, wi is not going to be in L, so L is not context free. Okay, so that's the very high level way of seeing it. So I have an example here, which I'm not going to do because I'm not going to have time. But I just want to say, I just said that AN, BN, CN is not context free. So I hope no one's, they haven't covered this proof yet, because otherwise I'm going to bore some of you. What you would do actually, okay, so here you would pick W as AM, BM, CM. And now your decomposition is trickier. So now if you write W as, you know, a bunch of A's, okay, and then a bunch of B's, and then a bunch of C's, then what you're doing actually now, what you're doing is you're scanning. So I know that all of this has length at least M, right? Because it's, in fact, it's exactly 3M. What you're going to do is, since your decomposition is, you're not going to get this right, UVXYZ, is UVXYZ, you're going to scan all of your string using VXY, basically. So VXY, the first possible case is VXY could be within all of your A's. So that's one case. So then you would pump up or down and try to get a contradiction. Then you could move your filter here, basically. It's kind of like a filter. And now your VXY would be all B's, okay? Then you could move it here. Your VXY would be all C's. And then you keep going. So now there is the issue where maybe you can have the V is has A's, and then it has B's. And then you have X, Y, and B's. So that's another case. And then you keep going. So the other case would be your V's are within the B's and C's. And then you have X, Y, yeah. So again, you would pump up or down. And you sort of keep going until you exhaust all the cases. In this case, that would be the last case, because you couldn't say something like V is, you can say VXY, V is A's, and then B's, and then C's. Let's say you can say this, because then your string would be, would have length kind of greater or equal to M. So anyways, it doesn't really matter. I mean, you haven't seen this in lecture yet, so I don't expect you to understand what I'm saying, but just maybe so you're not super confused when he's talking about it in the lecture. That's kind of a rough overview of what's going on. So what we'll do in next tutorial is I'm gonna just, I mean, if you guys wanna maybe try this as an exercise once you're done the lecture, you could do that, but I'm gonna go over it. I'm gonna go over this example next tutorial, and then I think 2 more examples, because these are quite long to do. So yeah, so next tutorial, I'm just gonna focus on pumping lemma for context-free languages, because I'm not gonna have time to cover Turing machines. Okay, so okay, so that last part probably wasn't very useful. Sorry about that. I just wanted to give you kind of a glimpse of the pumping lemma. But are there any questions regarding anything that we just talked about, or anything else? Nope, no questions. All right. Okay, well, in that case, oh yeah, and just a reminder, by the way, the tutorial on November 30th is pre-recorded. So tutorial 12, that's just a reminder. And there's going to be a Q&A session to make up that tutorial on December 4th from 2:30 to 3:20. So the reason is I'm also a student, and the end of the semester is also very rough for me. So that's why I'm going to have to pre-record the tutorial and answer any questions you have on December 4th. All right. So I hope you have a nice week, and I'll see you next tutorial. All right. See you, everyone.